these data came from a twin study. So each case is somebody with Parkinson's disease, and they have a twin who does not have Parkinson's disease. So we have these case control pairs that are correlated by the fact that they're within a twin pair. So we have correlated data here. Our outcome here is binary. You have Parkinson's disease or you don't. Our exposure variable, our predictor variable, is whether or not you've been exposed to various chemicals. So we have essentially categorical data for both the predictor and the outcome, but we have this correlation. So that's going to tell us that we're going to have to do a McNamar's test. However, if you look carefully at a lot of the cells, remember for a McNamar's test, we only care about the discordant pairs, which would be these middle two columns. If you look at all of these columns, a lot of the columns involve sparse data. So 1 or 2 people only in some of those cells. So not only do we have to do a McNamar's test, but we actually have to do an exact test to calculate those probabilities exactly, rather than using a normal approximation to the binomial, which is what a chi-square normally would do. So we're going to use a McNamar's exact test here. This question asks you specifically about the probabilities for PRC. It's asking you to calculate the p-value for the PRC chemical column. It might be helpful here to draw a 2x2 table if that helps you to see the problem. So we have your either, we have cases. The case is either, these are paired data, so we have cases and controls. So the cases have Parkinson's, the control is their twin, and we're analyzing things at the level of pairs. So we have, in this case, then what we're looking at here is you were either exposed to PERC or you weren't. And some of the cases both were exposed, some of they weren't, both were not exposed. Others, there was a discordance. So it turns out that the majority were not exposed. So we had 93 pairs where neither the case nor the control was exposed. There weren't any pairs where both case and control were exposed. However, we did have a couple of pairs where there was discordance. So there were 5 pairs where the case, that is the person with Parkinson's disease, was exposed to this chemical, but the control was not. And we have one situation, one case, where the opposite was true. The control was exposed to the chemical, but the case was not. It turns out for McNamar's test, the only thing that's of use, the only information that's informative for us here is the discordant pairs. So we have 6 discordant pairs. And the null hypothesis here is that the chemical is not related to whether or not you're a case or control. So under the null hypothesis, we've got 6 discordant pairs. If there was no relationship between the chemical and getting Parkinson's disease, this would follow a binomial distribution. X would follow a binomial distribution, and the n here is 6, which is just determined by how many discordant pairs we ended up with. The p would be 0.5 under the null hypothesis. In other words, just think intuitively, if there's no relationship here between the chemical and Parkinson's disease, you'd expect the discordant pairs to kind of be even, about 3 where it was the case that was exposed and not the control, and 3 where it was the control that was exposed and not the case. Well, the question we're really asking here is, how far off is a 5-1 split from what we'd expect under the null, which is a 3-3 split? So we're on a binomial. We're going to have to, because there's small numbers, we're going to have to calculate that exact binomial probability. So we're literally going to go through and calculate the exact binomial probabilities here. So what did we actually see? We saw the case where we ended up with 5 discordant pairs where it was the case who had been exposed and not the control. The binomial probability would just apply our binomial probability formula here. We've got 6, choose 5. P is 0.5, so we do 0.5 raised to the 5th, and then 1 minus p is also 0.5, so we do 0.5 raised to the 1st. But remember, p-values, we have to calculate the probability of what we saw and everything more extreme. So we also have to calculate the probability that we could have gotten all 6 discordant pairs. It was the case that was exposed. So we do 6, choose 6, 0.5 raised to the 6th. We also have to consider the other tail. Remember, if we did out all the binomial probabilities here, they go from 0 to 6. We get something that, excuse my crude drawing here, but we get something where we have 5 and 6 in one tail, but we have to consider we want to do a 2-tailed hypothesis and consider we could have been just as extreme in the other direction. That is, we could have ended up with only 0 or 1 discordant pairs where it was the case that was exposed. So we have to do a 2-tailed probability. You can do that by calculating the other tail, which is the probability that x equals 1 and the probability that x equals 0. It turns out that those are exactly the same as the ones that you see here. So this one comes out to be 0.015625. This one comes out to be 0.09375. This one will also be 0.09375. It's symmetric, and this one will be 0.015625. When you add all of those up, you get that the p-value here is 0.21875. This is a situation where we have paired data. We have repeated measures. It's the same women measured before and after they smoked. We have a continuous outcome, which is blood pressure and also heart rate. And so we're going to be using a paired t-test here because it's a before and after with a continuous outcome. The correct answer here is false. You actually cannot calculate the paired t-test here from the data given in the table. Why is that? Well, we're given the mean before smoking and the mean after smoking, but remember the paired t-test looks at the differences for individual women, and right now we don't know the difference values for individual women. We don't know how much each woman individually went up or down. We would need that information and be able to calculate the paired t-test. In this question, breastfeeding is a categorical variable. We're comparing groups of men by whether or not they were breastfed or the duration of how much they were breastfed. Our outcome variable is binary. You're either obese or you're not obese. We also do not have sparse data. So we're going to be using a chi-square test, and because we don't have sparse data, we don't have to worry about the Fisher's exact test or doing an exact test here. In this case, we're going to be comparing different groups. We're comparing men in different groups of duration of breastfeeding. So that's a categorical predictor, groups. They are independent groups. Our outcome variable now is BMI. BMI is a continuous variable. We're going to assume that it's normally distributed or close enough with such large sample sizes that we can run an ANOVA test here. So this question says, let's say we do our chi-square test for obesity and breastfeeding group, and we get a significant p-value. P is 0.03. What does that mean? Well, the chi-square test is a global test, so it actually doesn't tell us where the differences lie. It just tells us that at least one of those breastfeeding groups is different than the others. And if you actually look at the numbers here, it goes from 9.6% obese to 13.1% to 20.7%. It looks like it's going up as you get more breastfeeding, and then it goes down for the really long breastfeeding group. So there's no particular pattern here. So all we can conclude is D, that the percent of obese subjects differs in at least one of those breastfeeding categories. This asks you to calculate the mean change in exercise duration, and you can do it just off the graph. It's nice that they were measured in only in units of 0.5, nothing finer than that. So for example, this first person went up 3 seconds, the next person went up 0.5, this one was 0, 0.5, 1.5, 0, 1.5, 0.5, 0.5, 1.0, 0.5, 0, and 0.5. You literally just have to pick those up off of the graph. Well, if you add up all of those numbers, I'm not going to write it all out here just because it would take a while, but if you add up all of those numbers from 1 to 13, you end up, and then divide by 13 to calculate the average here, you end up with 0.77. To calculate the standard deviation of change here, we're simply going to take each observation and subtract it from the mean. Well, you already calculated the mean to be 0.77. So for example, we take the first person, subtract the mean, square that. Then we do this for the next person. The next person has a value of 0.5, subtract from the mean, square that. We're going to do that for all 13. I won't write it out completely here. You're then going to divide by n minus 1. For the standard deviation, you always divide by n minus 1, so that ends up being 13 minus 1, or 12 here. And then we would square root that whole thing. When you calculate that out, you get a value of 0.83. To calculate the standard error of the change here, we would take the standard deviation for change, which we calculated already as 0.83, and divide by the square root of n. So 0.83 divided by the square root of 13 is 0.23. That would be our standard error here. To calculate the 95% confidence interval, we're going to take the observed mean, which we already calculated to be 0.77. We're going to add and subtract our t-value here for a 99% confidence interval I gave you is 3.055. We're going to multiply that by our standard error, which we calculated already to be 0.23. When you add that all out, you're going to end up with a confidence interval of 0.067 to 1.47. The answer to this question is true. It is statistically significant at the 0.01 level. How do we know that? Well, we just calculated the 99% confidence interval. That confidence interval does not include the null value, which is 0 here. This excludes 0, therefore we can be sure that the p-value is less than 0.01. The answer to this question is false. We did prove that there is a statistically significant increase in the exercise duration of these patients. However, it's unclear if the camp is responsible for this change. They could have all gone up for other reasons. We don't have a control group here, so we can't conclude causality here. We just know that for some reason they went up a significant amount.